Recording in progress.
So, Hitesh KV, am I audible?
Yes, sir, you are.
Okay.
So can I ask what are we going with through today?
So, we'll be going through, first of all, is my screen visible?
Yes, it is.
Yeah, so we'll be going through some document which was shared to sort of revise what was taught in week two, as well as we will be solving some previous year assignment questions. And in case you have any doubt, you can ask helpfully.
Sir, so I have this doubts in week 3. So I needed some hints to go with the questions.
Week three. Acha.
Yes, week 3.
So what's your doubt?
I'm not getting the approach, sir. Not getting the approach to solve questions. I got the first one. The second one I'm finding a little bit difficulty on what kind of perspective should I look into to solve the question.
Acha. Mhm. Mm, yeah. Actually, we are not supposed to help you solve the assignments. That's the problem. That's the thing. So, in case you have any conceptual doubt or something,
No, sir,
what
the
that
concepts I get.
that is related to what concept?
It's based on solving the circuit based with differential equations.
Hmm. Okay.
So I'm not that good at math. I understand physics concepts, electricity, everything. I'm
Hmm.
very thorough with the first and second week.
Hmm.
The third one, I'm not so sure.
Okay. Okay. Acha. Mhm. This sort of maths.
No, this I'm clear with.
This you're clear with. Okay.
Yes, yes.
Mhm. I don't know because we are not supposed to help you solve the assignments. We're just there to teach some concepts as well as we will solve some previous year assignment and we will show how it's done. That is our job actually.
So maybe we can go through examples of week 3, if possible.
Week three now.
I don't want the exact solution. No, just the week 3 type of solutions. Example.
Acha, 1 minute. Like this.
Yeah, yeah, yeah.
Okay. Hmm. Okay. So you tell me how will you start solving this?
So I learned of deriving an equation. So which
Hmm.
is sum of forcing function and the constant function.
Okay. Uh,
So first I'll apply a KVL loop
hmm, okay.
and convert it to differential equation form,
Hmm,
and I'll get the root m plus a something. So
okay.
a1 will be equal to the first part. Uh,
The
it will
constant.
be equal to, yeah, constant a1 into e power rise to something, e power minus something, the constant that we get for the first mesh.
Okay.
Am I right?
No, no, no. First, like, I'll just show you some whatever. Basic thing is, you're going first. You have to get it in steady state. Initially, it was in steady state. Okay. The whole circuit was in steady state before the switch was closed at t equal to 0. So before the switch was closed at t equal to 0, that means there was current flowing like this. Okay.
Yes.
So what was that? What you'll have to first find out what was that value of current. Okay. What
Yes,
is
the
the
maximum current.
it will be the maximum. That is 12 by 20.
So yeah,
Okay.
so it will be R by L, so 12 by 20.
Yeah, yeah. That's it. Deepak Kumar, you're having network issues or what?
Sir, voice is not coming, so that's why I will leave.
Okay, but now my voice is audible.
Yes, sir.
Okay. Okay. So yeah. Fine. Okay. So you know the initial value of this. Then you will be closing the circuit equal to 0, and there's a resistor over here. Yeah. Mhm. No, like once you close the circuit, what will happen? These two resistors will come in parallel.
Yes, sir. Yes.
So you will find the
I
effective
understand
resistance.
that at steady state, I understand that at steady state, the 4 Henry inductor will act like a
One
short
second.
circuit at
Yes,
steady
yes.
state.
Yes, yes.
So it will be normal current dividing in the two branches. That is one,
Yes,
the
yes.
12 ohm branch and the 8 ohm branch.
Yeah.
So I can find out the current I1 and I2, but
Yes.
I don't know how do I get it to the expression I1 and I2 so that I'll know what is A1 value and B1 value.
I, this is very simple, man. See, A1 is the steady state value. A1 is the value
Okay.
of steady state because as t tends to infinity, this will die out. Okay, so A1 is the final steady state value.
Okay.
Huh, that is the steady state value. So first, what you do is like how I will work with this is the 12 ohm and the 8 ohm, which I'll see. So there's this 12 ohm resistor and there's this 8 ohm resistor. Okay, so I'll find the effective
Yes.
resistance. 12 plus 8, like that, I'll find the parallel effective resistance. Okay.
Okay.
Then
Okay.
we then we know that there's an inductor and there's a resistor in the circuit. Okay. So we will know what will be the what do you say? The form of the equation will have a time constant of minus RT by L.
I'm so sorry I did not get you. There was a slight network issue in the between.
Oh, network issue. Acha. No, so what will happen is there'll be a in the after t after the switch is closed, these two resistors will be considered. Okay. See, these resistors are not energy storing elements, so it just depends on what current will flow. So you will find the effective parallel resistance, and then you will find the current through the inductor. Okay, you will find the current through the inductor. You will get it as 20 minus 4 di by dt minus I into R, effective parallel resistance. Okay,
I
it has
into effective parallel. That is 1 by, okay.
Okay.
1
This
by 12 plus 1 by 2, then again reciprocate. So I'll get the effective resistance value. So I into that resistance value. Okay, in that equation. Okay.
you do this, there'll be some resistance I. Okay.
Yes,
This is the
yes.
resistance I, this is the inductance. So you will get like
Yes, yes.
20 minus 4 di by dt minus I into R parallel. Okay. This is
Yes,
equal to
yes,
0.
yes.
Then you solve this
Yes.
differential equation. Okay. You will get a value of I of
Okay.
t. Now you got this
Ah, yes,
value of
I'll
I.
get the value of I2.
Then you have to just apply
But there
that.
are two currents, I1T and I2T.
Yeah. So this is this current I of t. Okay. This is the current I of
Okay.
t we have found from using the differential equation. Now you want to
Okay.
find I1t as well as you want to find I2t. So it is simple.
Yes.
I1t will be equal to the resistance in the other branch divided by
Mm-hmm.
12 plus 8 into I of t. Okay.
Mm-hmm. This is the current division rule
Yes, current division rule you have to apply directly.
directly. So I'll get the current I'll get the current I2
You'll
with
get a
this
current
equation.
I1t and I2t you will get both. This is giving you
Yeah,
current
I1T and I2T. So I
yes.
know the value of I1T and I2T, and I'll know the value of e power minus K1 constant.
Yeah.
And how will I know A1 and B1?
That is simple. It is see. You will get
So should I apply KVL to each mesh, or how
no.
should I do that?
See, I told
No,
you. Deepak, you are saying
you
something?
have two unknown. You have two equation and unknown. You can easily solve that equation.
Yes. So let me explain. So I of t will be equal to some a plus b of e to the power minus k t. Okay. This
Yes,
is
yes,
I of t. I get this as I of t.
yes.
Then I will do
Mm-hmm.
I1 of t will be equal to 8 upon 20. 8 upon 20 into I of t.
Mm-hmm.
That will be this 8 upon 20 into I of t. What does this mean? I am just multiplying I of t by 0.4. If I multiply I of t by
Mm-hmm.
0.4, I will get I1t.
Okay.
So you know this A and you know this B. So this A1 will be 0.4 into A and B1 will be 0.4 into B.
So I'll tell what I understood by this. Is that fine?
Yeah.
Okay. First, I'll find the amount of current with the effective resistance. So that will give me the value of root, that is K1.
Yeah.
Correct?
Yes.
Is K1 equal K2 then?
Yeah.
Okay. Then I'll at infinity, I'll get a constant value of IT. By the current division rule, I'll get I1 and I2.
Yeah.
So here I'll be knowing K1 and I1. Right.
Yeah.
So at t power infinity, I'll get I1 is max. That whatever the value of I1 I found out will it's at t equals infinity. And so that e power minus infinity will be 0. So now I'll get the value of A1.
Yeah.
And then then I'll be able to easily find out the value of B1 by rearranging the equation. So that goes for both the equation. Okay. Okay. Thanks a lot.
Yes. Okay. So I'll go back to teaching what week 2 we were supposed to do. So leave this.
Okay.
Okay. So week 2. Okay. So Deepak, what is an electrical circuit?
Sir, electrical circuit is a combination of element and sources. This
So
is a closed.
tell.
Sir?
Continue. Keep telling.
A circuit is containing of many closed loops.
Okay. So it has some elements as well as some sources, right?
Yes, sir.
So what are the elements which are there?
Resistor, capacitor, inductor.
Okay. Resistor, capacitor, inductor. Okay, so that's fine. And what are the sources?
Voltage sources, current
Voltage source,
sources,
current.
Okay.
voltage dependent sources, current dependent voltage sources.
Okay. So there's a there could be a voltage source, there could be a current source, there could be a dependent current source, dependent
Independent.
voltage source, or independent one. Okay. So like that we can have sources. So electric circuit consists of elements and sources, and these elements, they are passive or active.
Passive,
Why?
because they cannot supply the energy infinite duration, for infinite duration.
Oh. But capacitor and inductor are storing energy. They can store energy.
As stored energy, but they are stored for some moment, not infinite duration.
Okay, fine, fine. Okay. So in this week, we will just be considering a passive electrical network, and also we will be considering only independent sources. Okay. And this week,
Yeah, before going ahead, can I ask a doubt? It's been
uh,
there for a long time now.
yes, yes.
Just about this passive and active elements.
Hmm.
Why is transistor considered as an active element? Because it's not. I don't actually get the definition of active element. Means like, I think that what I know till now is that an active device is something that can provide its own energy store for a finite, for a long period of time. Am I
Hmm.
right?
Um,
So transistor is just taking power from DC source and amplifying the signals. So
hmm.
I did not get why they are considered active elements, even though they store or produce their own energy.
Yeah. So it's not like they, yeah, like you said, what is correct, that they are taking the power from the DC biasing circuit and they're amplifying the signals. That is the way the transistor works. Okay. Uh, so it is, in a way, it is what do you say? It is not producing its own energy and all, that is correct. But it is able to, what do you say? Mm, let me think. Good doubt you have. It is actually able to amplify the signals, so that's why we call it amplifier. Hmm. I don't know this. I'll have to go and I'll get back to you. Okay. This doubt I've not considered.
Yes, sir. Because I have been wondering for a very long time now. I have not got any satisfactory answers even with my professors. So
Yeah,
I
actually,
just thought I'd ask.
there will never be anything which is which can provide infinite energy as a whole.
Yeah, yeah, yeah. I
Like
understand that.
any voltage source is actually dependent. There's some mechanical energy is being converted to electrical energy, and then you're getting some power, electrical power. That is there.
Yes, yes.
So nothing can just produce anything like infinite something.
So
So
can I ask what is the actual definition of active source?
mm,
An
active
active
source,
element, I mean.
active
Active
element.
element, active element.
Right now, I'm not. I don't remember actually. Yeah, it's there.
Oh,
No,
okay. Okay, sir. Thank you.
Mm, okay. Okay. So in this week, mainly we will be considering the inductors, capacitor, resistors. Okay, and we will be considering only DC sources. Okay. So when there are DC sources, uh, also we will be considering what is known as some sort of switching which is happening in the networks. Okay, there are some certain switching which is what do you mean by switching?
Maybe power on and off to certain branch of the network.
Yeah, like so like a switch is either closed or it is open, so that is there. So what happens when a switch is closed or opened?
open circuit and short circuit. There will be some mechanical system is arranged.
Hmm.
If we push the button, then they are connected to the wire, and they act as a short circuit.
Hmm. Oh no, that is okay. That is how what is happening mechanically. But in the electrical circuit, what happens when you open a switch or close a switch? What exactly is happening?
Exactly
The
happiness.
the current path gets built or destroyed.
Like in a way, the electrical network is changed. Okay, it was earlier some other electrical network. Now you have brought a change in the electrical network. Okay, by either opening or closing a switch. Hmm. Also, the as we know that the capacitor and inductor can store they are energy storing elements. So there is a concept of the initial value of initial value of current for an inductor, and initial value of voltage for a capacitor. Hmm.
Yes.
Yeah, so this also concept is there in this one. Then we also have to consider the final steady state value. The final steady state value of either the inductor, of either the current or the voltage. Okay, that also we will consider. Hmm. So these are some things we will look into in this session. Yeah. So there is this circuit elements. So an electrical circuit or network will consist of sources. Okay, we know there are three basic circuits are RLC. Huh? Like an inductor, capacitor, energy storing, while a resistor is an energy dissipative element. Also, there is one thing to note that for resistor doesn't have any memory. Huh. The value of the current flowing through the resistor directly depends on the voltage which is applied across it. While for inductor and capacitor, the previous values of either the voltage for a capacitor or the previous value of current in inductor, they play some part. Okay. So, mhm. So now these are the voltage versus current relations for RL and C. Hmm. So for a resistor, it is simple V equal to IR. So it just doesn't have any previous information which is required. No previous information is required. Now for an inductor, it is V equal to L di dt. So does the current lag the voltage in an inductor or does it lead?
Current lags.
Current lags. Okay. While for a capacitor, the current will lead the voltage. So this is how they vary. Okay. And these are the things for inductance V equal to L di dt and capacitance I equal to C dV upon dt. Okay. These are some things inductor fine. Okay. So what is the equation for the inductor? The voltage across the inductor?
L di by dt.
Okay.
L
So
di by dt.
V equal to L di by dt. Now suppose the current is constant, then what will be the voltage across the inductor?
What?
Suppose the current is constant, it has a constant value.
Zero.
So that means in case the current has a constant value, then the voltage across the inductor will be zero.
Yes, sir.
Now that's why when we consider DC, like DC means the frequency is zero. Okay. DC means frequency is zero. So that means the
Yes,
current
sir.
will be constant. That means the current will be constant. So for DC, the frequency is zero. That means the current is a constant value. It does not vary with time. That's why the voltage across the inductor comes out to be zero. And so for a DC circuit, in steady state, we consider the inductor to be act as a short circuit. Okay. To act
Okay.
as a short circuit.
Yes.
So this is one concept. Then now inductor, the current through an inductor does not change its value immediately. In an instant, it cannot change its value. So what will happen is at a time of switching. Now there was some circuit. Let us suppose this is some circuit. Okay, this is a battery. This is 12 volt. Okay, there is some inductor over here. There's a switch. There's a resistor over here, and there's one more resistor over here. Okay, this is R1. This is R2. This is L. Okay, this is IL. Huh? So this is the electrical network. So initially, at when t is less than 0, that means t equal to 0. At t equal to 0, what will happen? This switch will be closed. Okay, at t equal to 0, the switch will be closed. So before that, the switch was open. Okay, so we will consider that before t equal to 0, the switch was open, and the current will flow like this through the inductor and through this resistor, and it will come back. Okay, it will come back. So there will be some value of inductor current. So that inductor current, what will be the value? Deepak, what will be the value of inductor current before the switch is closed?
0.
Before
What,
the
sir?
Before this switch is closed, what will be the value of inductor current?
It will be R by 12. R1 by 12.
Yes, no, 12 by R1. 12
Yeah,
by R1.
12 by R1. So before the switch is closed, the inductor current is 12 by R1. Now, when I close the switch, so this is the value of inductor current. So it is at 0 minus. Just very short duration before the switch is closed, the inductor current is 12 by R1. Then when we close the switch, okay, at that instant, when we close the switch, it is known as denoted as 0 plus. Okay, and so at that instant as well, the inductor current will be 12 by R1. And then further it will change depending on the network. So so any doubts in this?
No, sir.
No, sir.
So Parth, Sarthi, any problems? Okay. So that's why the current through an inductor does not change instantaneously. And in case, okay, so that's there. And as well as what is the energy stored in an inductor? What's the formula for energy stored in an inductor?
1 by 2
Li
LV
square.
square.
Li square.
Li square.
Okay. So the current is at what instant?
I0.
I0. What about Deepak? What is your answer?
Current
Current at
is
12 by R1 at I of 0 means like when the time is I0 minus.
IF0 minus equal to IF0 plus equal to IF0, I0 equal to 12 by R1.
Okay.
Current will be same.
Okay, what about the energy in the inductor when time is equal to 1? Will it still be same?
What?
At time equal to 1 second, will the energy still be the same?
No. Energy will be different and change in any instant time.
Okay. So the energy across the inductor depends on the current which is flowing through the inductor at that particular instant.
Yes.
Yeah, so that will be the energy stored in the inductor. Okay. So now we also should be very careful that in case there's a current flowing through an inductor, like suppose the current was flowing like around 2 ampere or 3 ampere something, and then we do certain switching, And if we do that switching and like we just open the path of the inductor current, then in such a case, what will happen? Like just suppose there's an inductor, some current was flowing through it. It had some path, like it had one resistor. Some path was there for the resistor. This switch was closed. Okay. This is some voltage which is applied. V.
Sir,
Huh?
I have doubt regarding
Regarding what?
what energy dissipated by the resistor.
Sorry?
What is the energy dissipated by the resistor?
Energy dissipated by the resistor. Is I square R
Yes.
into T, no?
What?
I square R into T.
I square R into T.
Hmm.
But sir, in the case of capacitor, the energy dissipated in also 1/2 CV square, and energy in capacitor also 1/2 CV square. So total energy is CV square delivered by the source. In it is I think it is independent from the value of resistor.
No. That is, see, the uh, energy stored in a capacitor is equal to half of CV square. And that is
Yes,
the
sir.
what?
And energy dissipated by the resistor half CV square, right? Half CV square. Why the resistor dissipated by the energy?
No. Energy dissipated by the resistor is I square R into T.
But sir, I saw in lecture of sir. So I think I have a doubt regarding this.
Oh,
I think mean why there is a T there, right?
why
See,
does it?
Sir,
energy is not equal to power. Power is something which is at an instant. Energy is at a
no,
total time duration the current passed through the resistor. Is
Yeah.
that
no,
was that your doubt?
no. I want to say that energy is dissipated by the resistor. It is independent from the value of R.
No. It depends on the value
No,
of
no, no.
R.
It depends.
How, sir? Can you derive that?
Sir, if you show him the equation of B into I, then substitute the value of I in terms of equation, maybe you'll be able to understand why it depends on the value of R.
No, actually, I have written this. Can I share the screen?
Share your screen. 1 minute. Where's that? Don't know where to go to settings. Right. Okay, try sharing screen. Did you share screen?
Sir, my screen is visible.
Hmm. Can anyone see screen?
No, no, I cannot.
I'll stop
I
sharing.
can see it. I can see it. I
Hmm.
can see it. I can see it.
Yes. Now.
Sir, this is all about uh, capacitor.
Huh.
Sir, you can say total energy dissipated in resistor W is equal to 1/2 CV square.
1/2 CV square.
Yes, sir. And total energy supplied by the source is a CV square. CV square. Total CV square.
What is the circuit? What is the circuit?
I guess this circuit is independent of resistance, any internal resistance.
No. Here is a capacitor and resistor. Here is a capacitor and resistor.
It's not clearly visible actually. Wait a minute. Hmm. No, there's an inductor also in the circuit, right?
Sir,
No,
here
sir.
is no source. So, sir, may I say something?
Yeah. Tell.
Hello.
Yeah. You're audible. Please tell. Talking now. Tell. Parth, you were saying something?
Hello.
Hello. Yes, tell.
Sir, in this circuit, there is a source is disconnected. So, energy stored in inductor, it will discharge. That's why this is happening in this case, which he is telling about.
Okay,
So
actually.
source is removed, so and the charge and the energy stored in the inductor that will dissipate in the form of heat.
It will dissipate in the form of
And
heat
Sir,
in the
in
resistor.
your question, there is a battery is there. So both are the two different cases.
Yeah.
hello, sir.
Yes.
Sir, this is a lecture number 15 of this course. This is the circuit containing of one resistor, one capacitor, and one source E.
Okay.
This is the expression of voltage V across the capacitor, and here is a IT, and there, and then you can say energy dissipated by the resistor W equal to 1/2 CE square. This is the lecture in the 15.
Okay.
And total energy supplied by the source W equal to 1/2 C square plus 1/2 C square. Total is that W equal to C square, where E is the voltage applied and C is the capacitor.
Okay.
So that's why I am asking.
Yes. Okay.
Sir, may I speak something?
Tell.
Yeah, so Deepak, in this case, I think you're asking the question related to dissipation of energy by the capacitor. Am I right?
Yes, I am related in and because sir is say that the energy dissipated by the resistor in case of inductor 1y Li square, I think, right? Yes,
Li
something
square.
there.
So your question is it independent of resistance?
Yes.
No, see, it is not
It is.
independent of resistance because finally that value of current depends on the resistance. The value of voltage across the capacitor finally depends on the resistance as well. So indirectly it is affecting. Okay.
And
sir.
a capacitor can only discharge the amount of energy it already has. Based on the resistance or a circuit it is connected to, it will take longer or shorter period of time.
Yeah.
And if you have gone to the lecture, you might have also been told that the amount of energy stored by the capacitor while charging is equal to the amount of energy dissipated by the resistor. So it takes half of the energy to lose to fully charge a capacitor. So, and capacitor can only discharge what kind of energy it has.
Okay, so actually this meeting will end in some around 2 minutes. So again, I will start the meeting. Okay, the Zoom has this 40-minute limit. So after this meeting will end, I'll again start the meeting. Fine. So you guys are again join.
Okay, sir.
Yes,
so
sir. Sure.
So there's still
Sure,
some.
sir.
So my screen is visible, right?
Yes, sir.
Yes, sir, it is.
Okay. Yeah, so these points just say the same concept. So the concept which we consider for the inductor, like the current across the inductor cannot change immediately. The same concept is applied for the capacitor as well. So the voltage across a capacitor cannot change instantaneously. Okay. And when an inductor carries currents, energy stored is half Li square. When a capacitor is carrying voltage, when a voltage is across a capacitor, the energy stored at that instant is half CV square. Okay. So this is there. So the meeting will end.
Sir,
Yeah.
Sir, okay, sir. We'll join again.
Yeah.
I have a doubt.
So you guys able to see my screen?
Yes, sir. Yes, yes.
Okay,
Sir,
so
can you go back to this, sir? This, sir.
Mhm.
Okay. Can we move a little up?
Mhm.
Okay. So yeah, you were actually telling this. I don't know. The conversation just got head in a different way. Firstly, the current of there will be IL current through the inductor at a steady
Mhm.
state,
Yes,
uh,
yes.
passing through R1.
Yeah.
And just when the switch is closed, there will be a current. Will there be a current drop? Because just because another resistance is included,
See, at that instant, the current still remains same. Okay, but once the switch
it
is
will remain.
closed, it will remain same because it cannot change. The current across an inductor cannot change instantaneously. Okay,
Okay.
so when the switch is closed, the current will through the inductor will remain the same, but it will then start dividing into this R2 and into R1. Okay.
Okay.
Initially, that inductor current was flowing through R1. Then, when the switch is closed, it will go through R1 and through R2. And because we have added some resistor, the inductor current,
Mhm.
its final value of inductor current will change depending on this value of resistor R2 and R1.
Mhm.
Okay.
Mhm.
So,
So building on this, suppose
Mhm.
the current is flowing through R1 through inductor L at steady state,
Mhm.
and suppose we do a switching mechanism such that
Okay.
a resistance which is equivalent of Rn on 1 2 is placed instantaneously. So will it not affect the total current passing in the loop and maybe cause to change in the current through the conductor instantaneously?
No, no. No,
Was I clear, sir?
like to what I understood, you are saying if R2 is equal to R1, then you are saying, right?
No, no, no. Yeah. So means like if let's just say there was R1
Mhm. Okay.
and suddenly we just increase it to R1 into 2, or maybe we place an equivalent circuit of equivalent resistance of R and R2. So at that
Okay.
time, will the current IL change instantaneously?
No, it will never change instantaneously. It will
Okay.
it will remain this at that instant it remains the same, but then finally it will decay or it will increase to some particular value. It will go from one steady state value to another steady state value. That's all.
Okay. So depending on the load,
Hmm.
the current that is the steady current, that is the steady current that is passing through the inductor will change, increase or
Yeah, yeah,
decrease
yeah,
depending
yeah.
on the load.
Yes, yes, yeah.
Okay. Thank you, sir.
Okay, so I think I had better start solving previous year assignment things because we are running out of time. Okay, so is this visible? Week 2 assignment 2 question.
Yes, sir. Yes, sir.
Okay, start solving this. Okay, so I can give the screenshot.
Sir, should we wait? The other students haven't joined yet.
Oh, they are not joined. Huh? Like one had
No, sir,
joined
they just
actually,
dropped.
then they left, I think. 1 minute.
Yeah.
They're not joined. Hmm. No, I think we can continue. Anyway, finally the recordings will be available so they can see actually if they want to, if they missed anything. Okay.
Okay, sir.
So, so my screen is visible, right?
Yes, sir, it is.
Okay.
Yes, it is.
Yeah, yeah, fine, fine. So the question is, there's a current, this is the current profile. This is the profile of the current flowing through a capacitor. Okay. So we have been told the current through an initially uncharged 50 millifarad capacitor. So what do you mean by uncharged?
In it will not. At I0, there is no. It's not charged before, so there is no energy or any potential or anything stored in the element.
Yeah, that means the voltage
It means
across the
at I0 minus or I0, the value of
no, not I0, at t
current
equal
is
to
0.
0, t equal to 0, not I0. At time
Yeah,
t equal to 0,
at T equals 0.
the voltage across the capacitor is 0. Okay, so it is initially, it is completely discharged. So this is the capacitor. So
Yes, sir.
they are saying to calculate the voltage in volt across the capacitor t equal to 1 second. Okay, they want us to tell what will be the voltage across the capacitor t equal to 1 second. Okay, so let us start solving this. So this is the current across the capacitor. So we know the equation. Current flowing through capacitor is given by C into dV upon dt. Okay. Then the voltage across a capacitor will be equal to 1 by C integration of I into dt plus Vc of 0 minus. Okay. Is this equation clear?
Yes, yes.
So this is a simple equation for the voltage across the capacitor as it varies. So now we want to integrate. We'll have to integrate the current, okay, from 0 to t. So now let us focus on the integration. The current is 1 by C, okay. Integration of 0 to 0.2, it will be phi into dt. Any doubt in this part?
No, sir.
Okay. So similarly for 0.2 to 0.4, it will be 10 into dt plus from 0.4 to 0.6, it will be phi into dt plus 10 plus 0.6 to 0.8, it will be 10 into dt. Okay.
Yes,
And
sir.
they have given Vc of 0 minus is equal to 0 because the capacitor is initially discharged. So we can ignore that now. So finally, the voltage across the capacitor is 1 by C, okay, into phi. So if I integrate this phi into dt, what will I get?
Phi into 0.2.
Yeah, I'll get phi into 0.2. For 10, what will I get? For this, for the second integral, what will I get?
10 into 0.2.
Yeah. Okay. Okay. Similarly, again, for this also I'll get phi into 0.2, and for this also I'll get 10 into 0.2.
Yes, yes, yes.
So
Yes, sir.
finally, I'm getting 5 plus 10 plus 5 plus 10 into 0.2. Okay. Now, the capacitance they have told us that it is actually how much? It is 50 millifarad. Okay. So it is 1 upon 50 into 10 to the power minus 3 into 10 plus 10, 20 plus 10, 30. So it is into 30 into 0.2. Okay. So we will further do simplification, and they want the voltage across the capacitor t equal to 1 second. It should be just in terms of V. So that will be 10 to the power 3 into 3 into 2 upon 50. Just sorry for that. That will be 100 into 10 into 6 upon 50. Okay. So that will be equal to 120 volt. So this will be the voltage across the capacitor. Now, this is the voltage across the capacitor at 0.8. Okay, the voltage across the capacitor at 0.8 will be 120 volt. And then further across it, that it will remain at 120 volt. Why? Because the current is not changing. The current is fixed. So as we know, the voltage across a capacitor is given by 1 by C into integration of I dt plus Vc of 0 minus. So from 0.8 onwards, the current is 0. So integration of this will be 0. But the capacitor has stored some value of voltage. And that value of voltage was 120 volt. So from point 8 onwards, the voltage across the capacitor will remain at 120 volt. So we can say at time t equal to 1 second, the voltage across the capacitor is 120 volt. Okay?
Yes, sir.
Yeah. So
Clear.
Hitesh, you're from which college?
Sir, I'm from Global Academy of Technology. It's in Bangalore, a third tier college actually.
Bangalore, okay. So you're a resident of Bangalore?
Yes, sir, I'm a resident.
Great. Nice. So now we have found the voltage to be 120 volt and that's correct. Okay. So now we will go to this question. So, yeah. So there is a 200 millifarad capacitor. Just give us.
Sir, can we get access to previous year assignment question and answer, sir? Is there any way?
I don't think you have access to that. I don't know.
Okay, so it would help us out to understand the problems and to solve it as well.
Anyway, you're seeing this recording, right? So you can actually see it off. That's why we are actually solving it. So,
Yeah, so I want to express the problem that I'm facing, sir. I get the concept very clearly. I understand the concept during the lectures, but
okay.
just when I see the assignment questions, it's like I did not learn anything. So at that moment, I just feel like that. So maybe if there was an example like such questions, so it would really help out to solve the further coming assignments. So I just asked out if there was any way.
I don't know actually, because this actually we were given specifically by IIT Madras that these are the previous year assignment questions and you have to solve those questions in the problem solving and doubt clearing session. So this is like a simple problem solving and doubt clearing session. That's the thing.
Okay,
so
sure.
we have just been intimated this information. So I'm moving according to
Yes, sir.
that.
Yes, sir. I understand. I understand.
Okay. So
Thank you,
now,
sir.
yeah. So this is the thing. There's a 200 millifarad capacitor. Okay. So the capacitor is 200 millifarad. Okay. Then the voltage across the capacitor varies as this. Vc of t is 5 volt till t less than 0. And then it is 5 into e raised to minus t from t greater than or equal to 0. So if we plot it, 1 minute. Let me just draw a plot. Okay, so this is T and this is the capacitor voltage. Okay, this is the capacitor voltage Vc of t. Let us consider this to be time equal to 0 instant. Let us consider this to be time equal to 0 instant. Okay, so till time is 0, the voltage across the capacitor is 5. Okay, it remains at 5. At time t equal to 0, some sort of switching has occurred in the circuit. And the voltage across the capacitor becomes 5 into e to the power minus t. It becomes 5 into e to the power minus t. That means it is decaying exponentially. So it will start decaying like this. It will start decaying like this. Go on. Okay. So this will be of the form 5 into e to the power minus t. So at time t equal to 1, okay, we need to find the voltage across the capacitor. Now if you will observe, this expression of the voltage across the capacitor maintains the fact that the voltage across the capacitor cannot change instantaneously. At time t equal to 0, just at the instant before t equal to 0, that is at t equal to 0 minus, okay? At Vc of t equal to 0 minus, the voltage is 5 volt. And at Vc of time t equal to 0 plus, again the voltage is 5 volt. Okay, because from Vc equal to 0 plus, the expression is 5 into e to the power minus t. So we substitute t equal to 0, so we get it to be 5. So any doubts in this?
No, sir.
Okay. Yeah. So that's how this equation is a valid equation for the voltage across the capacitor. Now the voltage across the capacitor at time t equal to 1. Time t equal to 1, the voltage will be equal to phi into e to the power minus 1. Huh? So now we have to find the energy in millijoules stored in the capacitor. So phi into e to the power minus 1, can anyone solve it and tell what's the value? No one's having a calculator.
I just got it 1 second. It's 1.83.
Okay. It's around 1.83 volts. Okay. So at that instant, the energy stored in the capacitor will be given by half into CV square. Okay. So it will be half into 200 into millifarad. Okay. That is into 10 to the power minus 3 into 1.84 square. Okay. So this is the energy. So now how will I write it as? Energy will be equal to 100. 2 and 2 get cancelled, will be 100 into 1.84 square into 10 to the power minus 3. Now they want the energy to be in millijoule. Okay. So this 10 to the power minus 3 represents the milli part. So now the effective energy will be equal to 100 into 1.84 square. What is 100 into 1.84 square?
33.856.
Okay. So it will be 33. What is
338.56.
Yeah, it will be
338.5.
338.56 millijoule. Okay. Because this 10 to the power
Sir,
minus 3
I have a
represents
doubt
milli.
here
Yeah, tell.
regarding this. So when
Hmm.
they ask the energy stored in a capacitor at t equals 1 second,
Hmm.
so we don't have to consider the amount of energy that it will have, the capacitor will have before t equals 0.
Yeah, so this is the concept which you must drive home is at an instant, at a particular instant, the energy stored in a capacitor is equal to half into CV square, and that V is the voltage at that instant. Okay.
Okay.
So we don't need
So
to.
half into C, if before, just let's say we are at the scenario where t equals less than 0. So what will be the energy stored? Is it 1 by 2 C into phi square?
Yeah.
Yeah. So will we not consider at that energy at t equals 1 second?
No. With that energy, we will not consider. See, if they want to tell what will be the change in energy, if they say change in energy, then we have to consider. Okay.
Okay.
But they're saying that energy stored at at t equal to 1 second. That means it should be just the voltage at t equal to 1 ka square into half C into V square at that particular instant.
So the capacitor is actually discharging after t equals 0.
Yeah, it is
Am I right?
discharging. Yeah.
Okay. Okay, sir. Yes, I understood it. Thank you, sir.
Yeah. Okay, so now they are saying we have to calculate the amount of energy in millijoule lost by the capacitor between t equal to 0 and t equal to 1 second. Okay. Now we want to find how much energy it lost. So we found that the energy at t equal to 1 second. Let me write this out. The energy at t equal to 1 second stored in the capacitor is 338.56 millijoule. Okay, this energy at t equal to 1. Similarly, the energy at t equal to 0 will be equal to half into C into V square at t equal to 0. So at V At t equal to 0, the voltage is 5 volts. So that will be half into 200 into 10 to the power minus 3 into 5 square. Okay. So that actually is 2500 millijoule. Any doubts in this?
No, sir.
So the energy lost. Okay, it has lost some energy because the voltage is discharging. So the energy lost
Yes, sir.
will be equal to E t equal to 0 minus E t equal to 1. That is 2500 minus 338.56. So what is that?
2161.44 millijoules.
Yes, correct. 2161.44 millijoule. Okay. Yeah. So what about Deepak Kumar, Gokul? Any doubts in this?
No, sir. No, sir.
No, sir.
Very great. You guys are so smart. Okay. So now this is the fourth question. Let us take a screenshot. Just hold on 1 minute. Responding.
Sure, sir.
At a steady state.
Sir, will it not be equal to the resistance across 10 ohm at steady state? Because
yeah.
at steady state, uh, it's an open circuit for capacitor.
Yeah, correct. So, wait a minute. So this is my network. Okay. Now they have told us they want to find the voltage at the steady state. Huh? So at steady state, what will happen? Because this is a DC source. DC source means frequency is 0. That means the impedance of the capacitor is infinite. Because the impedance of the capacitor is infinite, it appears as an open circuit. So at steady state, the capacitor acts as an open circuit. That means no current flows through the capacitor. So whatever current is flowing will flow through this resistor and it will flow through this resistor and it will close. So we will find the current across this current which is flowing at steady state. What will be the current flowing through the network?
0.04 ampere.
Yes. Okay, it will be 0.04 ampere. Okay, so what will be the voltage across the 10 ohm resistor?
0.4.
Yes, 0.4 volt. Yeah. So you guys solve the question instantaneously. Okay. Yeah. So now we want to find the power in milliwatt being dissipated in the 40 ohm resistance at the steady state. So what they're saying at steady state, you tell me how much power is being dissipated by the resistor. So how will you calculate that?
0.060 I square R.
I square R. Okay. So power is equal to I square R. What is I? I is 0.04
0.04.
and resistor is 40. So do the calculation, what do you get?
0.064
0.06.
watt.
So that is in watts. So you have to get it in milliwatts.
Watt.
Ah,
So it will be 64 milliwatt.
yeah, 64 milliwatt. Okay. So that's the way you can solve this. So this is a steady state. So any doubts, Deepak, Gokul?
No, sir.
Very nice. Now, this is a very interesting question.
Sir,
Yeah.
can I ask it out before we proceed further?
Yeah.
It's about concept.
It's
So
about
I just wanted to know,
Mhm.
uh, as the inductor gets charged, in what direction will it discharge? I mean, uh, the capacitor will discharge in the direction the current charged it. I mean, like whatever the current charged it, charged the
Mhm.
capacitor, the discharge will be in the direction to the opposite of the current. So
Yeah.
what will it be in case of inductor, sir?
Across
Was I
the
clear?
yeah, I understood. See, for an inductor, for a capacitor, what happens is while it is charging, the current is flowing into the capacitor. Okay.
Yes, sir.
Let
And
me
it's
just
discharging, it's in the opposite
yeah.
direction.
So let me just show. So we have a capacitor is like this over here. So this is a capacitor and both sides there's something connected. So when it is charging, the current will flow like this into the capacitor. It is flowing into the capacitor like this and it is increasing the voltage. Now,
Yes,
when
sir.
it is discharging, what happens is the current is flowing in the outward direction. And so the voltage will
Okay.
start reducing. That is for a capacitor.
Reducing.
Yeah.
Yes, sir.
Now, for an inductor, there's the same concept. There is a current flowing to the inductor, and that current is brought about by a particular voltage applied across the inductor.
Yes, sir.
So so we consider this to be the positive terminal, this to be the negative terminal of the inductor. That means when I apply a positive voltage, the current through the inductor starts rising. That is, the current starts increasing. Okay, that means the current starts
Yes, sir.
increasing.
Increasing.
Now, when we want to discharge the energy across the capacitor, we will apply a voltage in the opposite polarity. What will happen then? The current through the inductor will start reducing. Okay.
Okay. Okay, so suppose if there was current flowing into the inductor from the negative terminal, so what does that indicate, sir? Does it
No.
mean that
Forget.
it's been charged or discharged?
See, for a capacitor, it is gets charged or discharged depending on the current flowing through the capacitor. But for a voltage,
Yes, sir.
it gets energized or de-energized based on the voltage which is applied across it. So in the charging state, I apply voltage like this. In the discharging time, I am applying voltage like this. Okay.
Okay.
So see, actually over here.
So the direction will be the same in an inductor, just the polarity will change.
No, see, for here, in this case, like you see the inductor current was at some particular value, it will be rising. So it is rising means the inductor is getting more energy, it is getting energized. Okay. But when we change the polarity of the voltage, the inductor current will start reducing. But you must remember that inductor current could be still remain positive. Like it could be around here at 2 ampere. Here it could be at 4 ampere. Then here it will be at 4 ampere. Here it will be at 2 ampere. So the direction of inductor current has not changed. But the direction of the voltage applied across the inductor has changed. That's all.
Has changed.
Yeah. But now let's consider the capacitor. Here the current was flowing into the circuit. So because the current was flowing into the circuit, the voltage is increasing like this. This is for voltage. So say it was around 5 volt. Now it has become 10 volt. Then in this case, the current is flowing out of the capacitor. So what will happen from this 10 volt? It will start reducing and it will come to around from 5 volts, suppose. So the voltage across the capacitor is still having positive polarity. But it just depends on whether the current is flowing into the capacitor or flowing out of the capacitor. That's all.
So how do we represent an inductor which is being discharged with polarity sign?
How do we represent it being discharged? That actually is not very clear. Okay.
So how do we represent an inductor that is being discharged? So we have a circuit in which an inductor is being discharged. So how do we represent it in terms of circuit? And what will be the polarity signs as it is being discharged?
But have you? I've not come across a requirement to know all this actually while solving. But this is a good question. Like we
Yes,
cannot
sir,
say.
because this time this time we had such a question. Means like we had a question similarly. Week 2 assignment. This batch.
Mhm.
So there was a current which was flowing into the inductor
Mhm.
IT
Okay.
through the negative terminal. So I did find out the value of current.
Mhm.
Okay, so but the original answer it was supposed to be wa- became minus. So I found the answer to be in minus, but the real answer was plus. So just because of the confusion of the polarity of the current, I lost the assignment mark. So I just wanted to clear out it.
No, this
Was I
is
clear, sir?
yeah, I understood. Okay, that they should specify in the question, like which direction they want the current to be flowing. Suppose there's this circuit, and let's just okay, just suppose this circuit is there. Suppose there's if they specify that this is the direction of current, then you must consider that direction of current. Whether it is an inductor or capacitor, it doesn't matter. They will specify what should be the direction of the current.
Okay.
Okay. So now we will proceed further to this question. This is an interesting question. So let us see. Like see over okay, 1 minute. So you are able to see this?
Yes, sir.
Okay. So as you see over here, they have specified the direction of inductor current. I of t is like this in this direction. Okay. So that should have been specified in the question.
Yeah, sir. It just makes so much sense here because in the question we got this time, the current was coming from the opposite direction. Means like the IT was going into the inductor through negative terminal, and the graph had current, from the negative axis, from the uh, means like the current was negative initially.
Okay, okay,
So
okay.
that got me confused.
Okay. Okay, fine, fine. So now there's this inductor current, the profile, how the inductor current is varying. So initially it is at 0 at time t equal to -1. Then it is rising to 2 at time t equal to 0. Then it is remaining at 2 from t equal to 0 to t equal to 2. Then from 2 to 3 it is reducing from 2 ampere to 1 ampere. And then from 3 time 3 equal to from time 3 second onwards, it is continuing to remain at 1 ampere. Okay. So now we will have to write down the equations, so like the expressions of the inductor current with respect to time. So that is our objective right now. So let us consider the inductor current I of t. Okay. Inductor current I of t, we want to write it. So from time t equal to -1 to time t equal to 2, we need to find out the what will be the equation. So can anyone tell what will be the equation? Okay, what is the slope? What is the slope of this line, slope of this line?
2, sir.
Yeah, the slope is 2. Okay. And what is the y-intercept?
2.
Yeah. Okay. So y-intercept also is 2. So that's why we can just write, we know the equation of a line is y equal to mx plus c. Okay.
Let's
So that's
see.
why it will be 2 into t plus 2 from time -1 to t to 0. Is this clear?
Yes, sir.
Yeah. So we can also verify whether it is correct. So we put at t equal to -1. We substitute here, so it will be -2 plus 2. So it will mean 0. That means inductor current is 0. Similarly, at time t equal to 0, we put over here. So it will be 2 into 0, that is 0, plus 2. So at time t equal to 0, the current is 2 ampere. So that means what equation we have written is correct for this curve. For this,
Sir,
during this time.
sir,
Yes, yes, still.
M how sir 2 sir M.
Okay, m how it is 2, that is m is equal to y1 minus y0 upon x1 minus x0. Just suppose, okay, for any between any of these 2 points. Okay, so we consider this point t equal to 0, y is equal to 2, and the time actually at that time is 0. Okay, similarly at time t equal to -1, the value of current is 0. So that's why it is 2 minus 0. And then x0 at that time is -1. So that will be 0 minus -1. That is 2 upon 1. So 2. Is there any more doubt in this? Because it is a bit tricky. I can say that. Takes time. So Gokul, have I cleared it out or it is still confusing?
Clear sir.
Okay. So that's how we found the slope, and we know the y-intercept. It is very clear from the graph that is 2. So that's why y equal to mx plus c. Based on that equation of the line, we have written this, and we have also verified it by substituting the values at the time instance. Similarly, I of t is equal to 2 between 0 to 2 seconds. Is there any doubt in this?
No, sir.
Okay. Now we want to find for this equation. Okay, this is a bit complicated. Can anyone tell me how will we proceed with this? What's the slope? What's the slope?
1.
1.
No, sir, -1, -1.
-1. Okay.
-1 t plus 3.
Okay, we will do, it will be according to Deepak, it is -2 minus t plus 3, right?
Yes.
So, according to Deepak, the equation is -t plus 3. So, can you verify, is it correct or not?
Sir, just give me 1 minute.
Yes, yes, take your time.
Yes, it is correct.
What about Hitesh, Gokul? Do you think it is correct?
Yes, sir. Yes, sir. Got it.
Let's see, Baba. If we put time t equal to 3 and time t equal to 3 seconds in this, it'll be -3 plus 3, that is 0. But the inductor current is 1. This equation is not
Sir,
correct.
is it -t plus 1?
No. Still not solved. So actually this meeting will end. Okay, so then you join again. We'll continue this. We will wait for those who are joining. Taking some time. So let us wait. Okay. So Gokul, you are able to hear me? Okay, so I'll continue with this. Okay. So we have said, so we have to know what is the equation between time t equal to 2 to time t equal to 3 seconds. Okay. So if you just consider this line, if I extrapolate it like this, if I take it over here, where will it intercept? Can anyone tell me?
Four, sir.
Yeah, 4. Okay. That's why this will be minus t plus 4. Okay. At time t equal to 3, it will be minus 3 plus 4, that is 1. And at time t equal to 2, it will be minus 2 plus 4, that is 2. So the current will be 2 ampere at that time. Then from time 3 onward, t equal to 3 second onwards, the value is 1. For t greater than or equal to 3. Okay. So now we have found these equations for the inductor current. Now we will proceed further. We want to find the inductor voltage at Gokul, you have a doubt?
Sir, how will t plus 4 come, sir?
Okay. Let me just extend this line. Okay. This has a slope of 1. Okay. It has a slope of minus 1. That means between 2 to 3, between 1 second, it will decrease by 1. So if we go in the opposite direction, between 2 to 1, it will increase by 1. So at this time, its value will be 3. And from 1 to 0, it will increase by further 1. So at this time, it will have value 4. Is that clear?
Okay, sir.
So it's just a slope. At some value, it was 4 at time t equals 0. Then because it is a slope of minus 1, it keeps decreasing by minus 1. It keeps decreasing by 1 for every 1 second. So from 4 minus 1, it becomes 3 at t equal to 1. Then from 3 you do minus 1, it will become 2 at time t equal to 2. From 2 you do minus 1, it will become 1 at 3 time t equal to 3 seconds. That is just the way. Okay. So that is the way, and this is the equation for the inductor current. So now they are saying we need to find the voltage across the inductor at time t equal to minus 500 milliseconds. Okay, Deepak, any doubt?
Sir, I am not understand. Can you tell me again?
See, the slope of this line is minus 1.
Yes.
That means for a unit of 1 second, its value will decrease by 1. So at time t equal to 2, its value was 2. At time t equal to 3, its value has become 1. Is this clear?
Yes, yes.
So
Yes, sir.
if we go in the opposite direction, from 3 to 2, its value has increased by 1.
Yes.
So if you go from 2 to 1, its value will increase by 1. So it will become 3. Is that
Oh,
clear?
yes.
And then from 1 to
Yes, sir.
0, its value will further increase by 1. So its value will become 4.
4.
Okay. So
Okay.
4 is the y-intercept. 4 is the y-intercept. That's why
Okay,
using
okay,
the
sir.
equation y equal to mx plus c, it comes minus t plus 4.
Okay, sir. Thank you.
Yeah. So now we need to find the voltage across the inductor at time t equal to minus 500 millisecond. Minus 500 millisecond means minus 0.5 second. So what we will do, we know the voltage across the inductors V equal to L di by dt. Okay. So time t equal to 500 millisecond means I'm considering this part at this instant, at this point. So I will differentiate this equation. So if I differentiate this equation with respect to time, what will I get?
Differentiate, sir.
Yeah, because di by dt, right?
That will give a double order differential equation. Second order
No, this is the
di
this is
square by dt square.
no. We just voltage across an inductor is given by V equal to L di by dt. Is that clear?
Yes, sir.
So at time t equal to minus 500 millisecond, that means at time t equal to minus 0.5. Okay, at time t equal to minus 0.5. That is the instant when we want to find the voltage. At that time, this is the thing. That time the current is increasing in this form. So the expression is 2t plus 2. So now I'll have to differentiate 2t plus 2. Okay, when I differentiate that, I will get L into 2. Okay. So the voltage at t equal to minus 0.5 will be 2 into L. Any doubts in this?
No, sir. No, sir.
No, sir. No, sir.
So that is there. So L is value is 100 millihenry. So 100 into 2 is 200. And milli means 200 into 10 to the power minus 3. That means it will be 0.2 volt.
Excuse me, sir. Can we go back again?
Yeah.
Okay. Okay, sir. Okay. 2 is a constant. Got it, sir. Thank you.
Okay. Yeah. Now we will
Okay.
find.
Okay, sir. Okay. 2 is a constant. Got it, sir. Thank you.
Now we'll find the inductor voltage at t equal to 1 second. So at t equal to 1 second, the inductor current is 2, which is a constant value.
Yes, sir.
So when I differentiate a constant, what is the differentiation of a constant? What will
0.
0? That means the voltage across the inductor is 0.
Okay.
Okay. So for this question, seventh
Yes.
question, the voltage across the inductor is 0 volt. Now they're telling us to find the inductor voltage at t equal to 2.5 seconds. 2.5 is around here. So we will do further again. So we will further write V equal to L into di by dt. That is L into d of dt at minus t plus 4. That is equal to minus L. That will be equal to minus 0.1 volt. Okay. Any doubts in this?
No,
No,
sir.
sir.
No. Okay. So it is just simple differentiation. Okay. So this is the point. Now we will proceed to this question. Okay. This question we will go on to. Let us say, we take a screenshot. 1 minute. So Deepak Kumar, you are from which college?
Sir, I am from Prestige Institute of Engineering Management and Research, Indore.
Okay.
Sir, and you?
I am from IIT
I
Kharagpur.
Yes, sir. Okay. Fine.
Oh, you guys are not given all this information.
No, sir. Just told about the session timings and nothing else.
Okay. So I'm actually a PhD student at IIT Kharagpur. Okay. Yeah.
PhD?
In what are you specializing, sir?
Electrical engineering.
Oh, nice, sir.
You guys also will be from electrical department, right?
I'm from electronics, sir. I'm trying to pursue in VLSI.
Okay, good choice. Very nice choice. Yeah.
You said, did you have any idea?
No, I'm not. I don't know VLSI actually. It's
Oh.
above me. Yeah.
So no, in your student life, like in your BE, are you
No.
you are from BE, sir?
Yeah, I did BTech. Yes. That time I didn't know about
BTech,
VLSI.
yeah. So, acha, okay.
Yeah. But you're from electrical department, no? Electrical engineering.
Yeah, electronics.
No,
I'm
yours
from
electronics.
electronics.
Okay, then you'll get it. Mine was electrical, so our focus was not on electronics so
Yeah.
much. So we are not good. I'm not good at electronics.
Actually, we have a professor in our college, sir. His name is Professor Ravi Chandran. He is actually some sort of a scientist. Actually, he's been working with ISRO and many, with many VLSI confidential projects in DoD and all. So he just told me this thing. According to him, there is no derivative of electronics or electrical. Both are same to me.
Oh,
Sir, and I was like, actually, I avoided electrical engineering so much, but yet I have to learn all the concepts. So he told me that you can't just ignore anything. When you are an engineer, you have to learn. You need to know things from all aspects
yeah, yes,
of
yes.
engineering.
Yeah.
So
Okay. So let's proceed with this question. So we want to find the current IL in milliamperes at steady state. So what will happen at steady state? Can you tell in steady state what will happen to the circuit?
it's a short circuit, sir.
So short circuit. So that means no current will flow through the 4 kilo ohm source, 4 kilo ohm resistor,
12 milliampere.
12 milliampere.
12 milliampere.
Yeah, yeah,
IL
correct.
equals 12 milliampere.
Yeah. IL equal to 12 milliampere. Good. Nice. Similarly, we want to find the voltage VL at steady state. So what will be the voltage across the inductor then?
0, sir.
Yeah. Why?
At steady state, voltage is 0. Inductor acts as an short circuit.
Yeah. So the voltage will be 0. So Gokul, you are able to understand?
Sir,
Yeah.
IL, how sir? 2 milliampere. IL.
Okay, yes. So at steady state, this acts as a short circuit. Okay. That means all the current will flow through the inductor and will not flow through this resistor. Okay. So it acts as a short circuit. So the resistance which the current will see will be 2 kilo ohm. So that's why we will do 24 divided by 2 kilo ohm. That will be equal to 12 milliampere.
Sir, what happened 4 kilo ohm, sir?
Yeah, because the
Current
inductor
entering or
It will vanish.
current going or not? Sir?
yes, 1 minute. So because the inductor acts as a short circuit, so all like this current, suppose this is I1, this is IL, and this is I. So when the inductor at steady state, the inductor is in short circuit condition. So all the current I, all the current capital I will flow through the inductor. No, this current I1 will be equal to 0. Okay.
Okay, sir.
See, because you must remember the current will go through the path of least resistance. Least resistance is this because the resistance here is 0. It is a short circuit. Total no resistance is there. So that's why the current will flow directly across like this. Okay, this will just vanish. It will not
Okay,
be.
sir. Okay, sir.
Okay. So now we will consider this question. So this is the circuit, okay? This is the circuit which is there. So what are they saying? You want to calculate the voltage Vx, assuming that the circuit is running for a very long time. So it is, we assume that they told in the question, assuming that the circuit is running for a very long time. What does it mean it is running at very long time?
That means all inductors act like short circuit and capacitors are open.
Yeah, that's
So we
all.
can redraw the circuit.
Yeah, so that's why we have to redraw the circuit. So what will happen? This capacitor acts as an open circuit and this inductor acts as a short circuit. That's why we will draw it. It will become like this. Plus minus 5 volt, 20 ohm. This short circuit. This is open circuit. And this is short circuit. Okay. This is short circuit for the inductor and an open circuit for the capacitor. Then we have this 15 ohm resistor. This 5 ampere current source. Another 15 ohm resistor here. And we have this plus minus Vxy. 10 ohm resistor here, and this is the circuit. Any doubts in this messy circuit?
No, sir. At least for me.
Yeah, it's very untidy. I'm sorry. So this is the circuit. In steady state, this will be the effective circuit. Okay. So now, what we will, it's actually very bad, too bad actually. So I'll further draw it in again in a better form. Okay. So any doubts in this?
No, sir.
Vx will minus 57.
What? कहाँ पे?
I think Vx will be minus 57
Oh, you already solved it.
or no?
Yeah, it is Vx.
Vx.
No. This is
No,
Vx.
sir. Yeah, Vxy.
Yeah, Vxy is minus 57, correct. Okay.
Yes, sir. Yes, sir.
So how we will solve it is we will consider this current I1 like this here, and we will consider current I2 like this. So we will do mesh analysis. Okay. Now we must remember then
Sir, how?
Till there.
Sir, in this circuit we cannot use mesh analysis because there is a current source. There is a variable current source.
Yeah.
So we
Okay.
can use nodal analysis.
Okay, we can use nodal analysis. That also is there. But mesh analysis also is possible because we will get two equations for the current. We will not consider this inner mesh. These inner meshes we will not consider. We will consider the complete outer mesh. Then we will get two equations which we can solve actually. See over here, what do we know? We know I1 minus I2 is equal to 5. Is this clear? I1 minus I2 is equal to 5.
Yes, sir.
Then we apply KVL
Yes.
for the outer circuit. That will be 5 minus 20 I1 minus
Minus
15 I2
I2
again minus 15 I2. It's equal to
equal
0.
to 0.
Yeah.
Yes, sir.
Then we do 5 minus 20 into what is the value of I1? I1 is equal to I2 plus 5. So that is 20 into I2 plus 5 minus 30 into I2, which is equal to 0. So we solve it further. So we get it to be 5 minus 20 I2 minus 100 minus 30 I2 is equal to 0. So we will get it as minus 95 is equal to 50 into I2. So we get I2 to be equal to minus 95 upon 50. That is equal to minus 1.9 minus 1.9 ampere. Okay. So now we want to find Vx. Okay. Vx is the voltage over here plus minus Vx. So Vx will be equal to 15 into
Minus-
I2. Sorry. So that's why it will be equal to 28.5. 15 into
Yes, sir.
minus 1.9. So it will be equal to minus 28.5 volt. Okay.
Yes, sir.
Similarly, the current I1 is equal to I2 plus 5. That's why current I1 is 3.1 ampere. So the voltage Vxy, we can write it as So Vxy minus Vxy, and to the 10 ohm resistor no current is flowing. So the voltage drop across the 10 ohm resistor is 0. So minus Vxy plus 5 minus 20 I1. So it will be minus Vxy plus 5 minus 20 I1 is equal to 0. So we will get Vxy is equal to 5 minus 20 I1. Okay, that is 5 minus 20 into 3.1, which will be equal to 5 minus 62, which is equal to minus 57 volt. Okay, so any doubts in this?
Sir, can you please explain me the KVL equation, sir? How you put KVL equation
For this
while
one,
doing the mesh analysis?
for this
The
one.
first line,
Okay,
the very first line.
So I go from here to here. Okay, so plus 5 volt, 5. Then the drop across the resistor, that will be minus 20 I1. Then I will proceed further. It will be minus 15 into I2 for this resistor. Further minus 15 into I2 for this resistor. And then further the circuit is complete.
So we just open the 5 amp current source, sir.
See, 5 ampere current source we don't consider, no? Because
We don't consider.
because we don't know the voltage across a current source. That is why
Okay.
we cannot do the mesh analysis for the inner circuit, but we cannot apply KVL. Where's the pointer? We cannot apply KVL for the inner meshes. That's why we cannot apply KVL like this. Because we don't know the voltage across a current source. That is undefined. That is not known to us. Similarly, we don't know the current through a voltage source. That also we don't know. Okay, those things you must keep in mind. That's why we apply KVL across the entire mesh, across the entire circuit.
Yes, sir.
Okay. we have completed solving this question. Now we will proceed to this question. There are three more questions. Okay. So this is the circuit. Let me take a screenshot. So what they are asking is, the capacitor is initially charged to 10, that is VC0 minus equal to 10 volt. Then the switch is closed at t equal to 0. They're saying calculate the time required in seconds for the capacitor to discharge to 1 volt. Okay. So how will we proceed? Tell me. Anyone has any suggestions what to do?
Sir, we need to write the equation of voltage. The voltage across capacitor, instantaneous voltage across the capacitor. Then we can VC equal to 1. Then we can put VC equal to 1 volt and then easily find the value of t time.
Okay. Yes, correct. So the capacitor was charged to VC0 minus is equal to 10 volt.
10.
Then the equation of the voltage across the capacitor will be given equal to VC of 0 minus into e raised to minus t upon RC. Any doubts in this?
No, sir.
That's why VC of t is equal to 10 into e to the power minus t upon 100. Any doubts in this?
No, sir.
Yeah. So that's what, as he is, as Mr. Deepak Kumar has said. Okay.
Yes, sir.
As you have suggested, right? We will put VC equal to 1.
Yes.
1 equal to
Yes,
10
sir.
into e to the power minus t upon 100. So we can write it as 10 is equal to e to the power t upon 100. Then you solve this, what you will get?
No, sir. 1 by 10 आएगा. 1 by 10 will be in the left side.
नहीं भाई. This
नहीं, अब minus t na, minus t becomes
either
plus.
minus t. This is minus t. Na? When it goes to this side, it will become plus. So it will be 10 equal to e to the power t upon 100.
Yes, sir. I understood.
Okay. So what is the value of t then?
We need to take a log, natural log, ln.
Yeah. You take ln of 10 is equal to t upon 100. And if you solve it, you will get t to be 230.3 seconds. Okay?
Yes, sir, I got it.
230.3 seconds. Okay. We're done with that question. So now this question. Okay? So this is this, and we'll paste it. Okay, so this is the circuit. So let us read the question. The switch is closed at t equal to 0. So at t equal to 0, we close the switch. So before that, no current was flowing through the inductor. So the IL 0 minus is 0. So how much time is required in seconds for the inductor current to reach the value of 0.8 ampere? Okay, so we have how much time it will take for this inductor current to reach 0.8 ampere? That is the question. Okay. So now what we will do is at t equal to 0, IL at 0 minus is 0 ampere. Okay. Now we will apply KCL. KCL at this node. So this is 1 equal to
1 plus
V by R. Okay. Let us assume the voltage here is V of t. So this V of t upon R plus the current through the inductor. Okay. इसमें कुछ doubt in this? You have any doubt?
no, sir.
Now this V of t is actually equal to L into di by dt, because the same voltage is the voltage across the inductor.
Yes, sir.
So that's why I substitute V equal to L into di by dt. So I will get
By
1 L upon R di by dt plus I. Okay. This is t. This is t. So what will I get? I will get 2. No, I will get di by dt plus R upon L I of t equal to R upon L. So I will get di of dt plus 2 into I is equal to 2. Any doubts in this?
no, sir.
So there's that concept of integrating factor everything, right? So the integrating factor is equal to e raised to integration of 2 into dt. This 2. Okay. So it will be e to the power 2 of t. So then I will write I of t into e to the power 2t is equal to integration of this 2 over here. 2 into e to the power 2t into dt plus c. Okay. Plus some constant c. So when I integrate it further, what I will get is I of t into e to the power 2t is equal to 2 e to the power 2t upon t plus c. So I will get it is I of t e to the power 2t is equal to e to the power 2t plus c. So I of t is equal to 1 plus c into e to the power minus 2t. Any doubts in this simple differential equation maths?
No, sir.
So at time t equal to 0, what was the current? Current I of t was 0. So this is equal to 0 equal to 1 plus c. E to the power minus 2t at t equal to 0 is 1. So this is 1 plus c. So we get c equal to minus 1. So we can write it as new page it is. I of t is equal to 1 minus e to the power minus 2t. This is the current through the inductor, the expression for current versus with time. Now what we do, we are going to find the time at which the current is 0.8. So we put 0.8 is equal to 1 minus e to the power minus 2t. So we get e to the power minus 2t is equal to 0.2. So we write it as e to the power 2t is equal to 5. So 2t is equal to ln of 5. So we get t equal to what? Can you calculate and tell me?
0.8 millisecond. 0.8 second.
0.8 seconds.
We got it. So it is t equal to 0.8 seconds. Okay. Now we'll proceed to the next one. Now, how much is the total energy in joule delivered or supplied by the current source after the switch is closed? So how much is the total energy in joule delivered or supplied by the current source after the switch is closed?
1 by 2 Li square.
Okay. So what you'll get there? What is I?
1, sir.
0.8.
No, it will be 1. Steady state value, right?
Steady state value.
Hmm. Okay. So it will be 1 joule. The energy will be 1 joule.
Yes, sir.
So Gokul, any doubts?
No, sir.
Okay, anyone else has any doubts?
No, sir.
Okay, so I hope this session was useful to you in some way. Okay. And it will help you in solving your further assignments and everything. So I conduct this session every week, Monday between 6 to 8. So this is the time slot I have selected. Okay.
Yes, sir. Thank you.
Yes, sir.
Mhm.
Thank you, sir.
Okay. Fine. Then when do you guys have to submit assignment to?
Assignment 2 has already been submitted, sir.
Oh,
8.
already submitted. Oh,
Yes, sir. Yes, yes.
okay, okay. Gotcha. Okay, okay. So Gokul, you're from which college?
Panimalar Engineering College, Chennai.
Oh, Chennai. Okay.
Yes,
Even I'm from
yes, sir.
Chennai. Yeah. Okay, okay. Okay, then we can end the meeting since time is almost out.
So,
Okay.
sir, our week 3 assignment will be due on Wednesday. So, is it like we'll carry the session of the assignment which has already been submitted next week?
Yeah, yeah, yeah. It's that way only. They have,
Okay, sir.
because the main concern for them is that we must not help you solve the like assignment, like something I think they have told something.
No, sir, but if we face similar kind of problems, it would be easy to proceed.
Yeah, but this is the way we have been told to operate. We have been told to conduct.
Actually, last time I did attend Tuesday's session, sir.
Okay.
Tuesday 7 to 9.
Okay.
So the instructor there, I don't know, I forgot her name. So when we informed her about how due dates are done for assignment 1 and 2, and we won't get any problems for assignment 3. So she was like, this week, so she'll take few assignment 2 questions and assignment 3 questions.